Hey guys, today I'm going to be looking at probability in the probability sphere, specifically looking at tree diagrams, right? So where do we use tree diagrams, specifically multi-step probability scenarios? What does that even mean, right? It's where it's got multiple stages, right? For example, you flip three coins sequentially, one and then another and then another. You've got three stages, right, in that sort of probability scenario. So a tree diagram will show stages of an experiment where each branch represents a possible outcome, right? So the stages I spoke about, this is the first stage where you can either flip a head or a tail, right? And they've assumed there's an equal chance of flipping a head or a tail. So it's 0.5 because you put the probabilities along the branch and 0.5 this way. Now, one of the common things is that students might not check if their probabilities add up to 1 on each sort of stage, right? Now, they have to add up to 1 because 1 represents the certainty of an outcome. So in other words, it is certain that a heads or a tails will occur in that first stage, right? So 0.5 plus 0.5 is 1. Notice it's the same for this, where heads or tails in the second stage, or heads or tails in the third stage. It's going to be adding to something to 1, right? That's really key. So, I mean, it just represents all the possibilities, simply, right? So imagine we flipped tails, then heads again. So we flip the tails, 0.5, then heads, and then a head again. Now, what's the probability of tail, head actually occurring? Tail, head will follow that along. So tail, head is THH, we'll say, equals THH. And what I really recommend people doing is like actually calculating each of these at the end. So what does it equal? 0.5 times 0.5 times 0.5, or 0.5 cubed. 0.5 cubed. Now, why are we timesing the probabilities? Multiplying probabilities when they should add, or adding probabilities when they should multiply and. So the reason we multiply probabilities is because the reason we do it, right, is because when you think about it, tails, then the head, then a head. It's so you need to be sort of multiplying because you're relying on all of them occurring. It's not just this or this or this, right? So it's this and then this and then this. So they're all related and all need to occur at the same time. So that's really important. So that's why 0.5 cubed, right? Which equals, if I just get my calculator, 0.53, 0.125, right? So that's a probability of flipping a tail, then a head, then another head, right? Okay, cool. So this is an example of an independent event, right? Because one event is not going to impact the other. For example, if we flipped a head on the first time, it's not going to impact if we flip a head on the second time, right? Because you see how the probabilities are unchanging. It's independent, right? Then it's not depending on previous results. Same with tails. So this is an example of an independent probability event on a tree diagram, right? Now, what's the opposite? Dependent is where the first event changes the probability of the next event. Now, think about drawing, say, a king from a pack of cards, 52 cards. There's 4 kings. Probability of that is 4 over 52, right? And then what about drawing a king if we didn't replace it? It would be 3 over 51. Why? Because we've taken one king from the top, but we've also taken, a card from the denominator. -1 king, -1 card. So you get 351. So you see how it's dependent on the first event. So that's an example of dependent probability events. Cool. So hopefully that makes sense. Now, I guess I want to explain when we're adding probabilities when we should multiply. So what if there's a question saying probability of picking just one stage, this is just single stage, picking a king or actually picking a king or say queen. So king or a queen, right? What's the probability? So that's going to be the probability of king plus the probability of queen, which equals 4 over 52 plus 4 over 52. All right, that equals 8 over 52. Now, what if it was probability of king and then a queen. Because it's king and then a queen, if it was 2 stages, it's got to be probability of king times probability of queen, right? So it's going to be 452, all in brackets, times 452. Okay. That's because we're requiring both of them to occur at the same time, so we must multiply their probabilities. But or means that we can have either or. So we can just add the probabilities up and we can get in either of that sample space. Cool, let's go to these questions now. In a chess tournament, each contestant must play 3 others. Oops. I don't know what's happened there. Sue estimates that she has a 60 chance of winning a game. Therefore, what chance does she have of losing, right? Assuming we can only win or lose, of course you could draw in a chess match, but we'll ignore that. Win or lose, right? So win, comma L. If this event is certain is 1, and with 60% chance, 1 equals 0.6 plus something, right? It's win, and then what about loss? What does that leave loss to be? 0.4, right? So we know she's going to have 40% chance of losing, assuming there's no possibility to draw. So this is a bit of a limited one. So sample space for the possible outcome of Sue's having 3 games, right? So think about it, 3 games in terms of 3 stages. So how's it going to look? If she can only win or lose, and there's 3 stages, it's going to actually look very similar to this one. Instead of heads or tails, it's going to be win or loss. WL, WL, WL. So this is, say, she won, then lost. She won, then lost. Or, she lost, then lost, then lost. What you do is you put the probabilities on each of the branches, right? Obviously, I haven't done them here because I've been a bit lazy, but you should in your response, right? So we've done it, and we've listed the sample space for the possible outcomes. So here is the sample space. The best chance will also calculate that sample space, right? W, win, then win, then win. Given she's got 60% chance of winning, 0.6 times 0.6 times 0.6. Everything's cubed is 0.216, right? And WWL, she's going to win 0.6, win 0.6, lose 0.4, 0.144. Notice that's the same as this, is the same as this, is the same as this one. And then 0.96 is losing, so 0.4 times winning times 0.6 times 0.4. And then, yeah, that's how you calculate all of those, right? And then what's this question asking? On the probability of Sue winning at least 2 games. Okay. Winning at least 2 games. So she could win 2 games or 3. So she could win all the games or win 2 games. And there's 3 combinations, right? So what we need to do is, if you've done this working out, you can literally just pick the ones that it is. So it's, what is it? Win, win, win. WWL. WLW. No, this is 2 losses. Yes. No. 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 Now, why do we add the probabilities? Because these are different scenarios and we don't have to have them all occur at the same time. It's about adding different scenarios of the possibilities. So this is where she won all 3, or she just won 2 or 2 or 2. So we're going to add them up and we get this final answer. All right, cool. Hopefully that makes sense, guys, with those sort of questions. To sum up, tree diagram is for multi-step probability scenarios, as in you roll a head and then you flip a dice, or you flip a coin, then you roll the dice, or you flip a coin 3 times, right? The probabilities go on each of the branches. The branch, each sort of stage must add up to 1, right? Yeah, I think that's about it. Right, thanks, guys.